Correct.
So do we use that? Or do we
So
use-
first you find VRMS. Correct. You have to use this formula only, provided. So here you don't have VRMS, right? First you have to calculate VRMS.
Yes, ma'am. I got
How much
67.67.
did you get? 67.1 you'll get.
Yes,
Correct.
ma'am.
And VDC how much? 60.5 somewhere you got. Correct.
Yes, ma'am.
Substitute.
Oh, okay. Ma'am, isn't triple factor
Substitute.
just
Take a
V
square of it.
VDC?
Minus 1. VRMS by VDC the whole square. Minus 1.
Ma'am, but we can
That is
also
the formula, right?
by VDC, right?
Come again. Omisha, come again. Your voice is breaking.
Ma'am, it's also VAC by VDC, right? Why can't we do that?
VAC by VDC. Correct. You can use, provided VAC by VDC you can use. But the thing is that VAC directly you can't take the value as primary voltage. Correct. You have to find the RMS value of it and then calculate. So, in order to find ripple factor, we consider the total power and that we equate it to the power with respect to DC and AC.
Okay, ma'am.
With respect to that, we derive this relation. Correct?
Yes, ma'am.
So, use this.
Man, ripple factor is same for all rectifier this type.
Pawan, come again.
Man, ripple factor is same for all this type of rectifiers, no man.
Ripple factor, it should remain same. Approximately same. Say if it is not exactly 48%, you should get in and around 48% at least when you do the calculation.
Yes, ma'am, understood.
Okay. Yes. So we'll continue with today's session. So today's topic of discussion is filters. Yes. What is filter? Anybody? What is filter?
It is the device used to remove ripples from the
Arul,
rectifier.
are you want to reply? Whatever you type, it is wrong. Also, no problem. Anirudh Aryan, please respond.
Yes, ma'am.
Anirudh,
Yes,
are
ma'am.
you
Yes,
there?
ma'am. Anirudh is there.
Yeah, Anirudh, tell me what you know about filter.
I just have like I can't explain in words, so I'm like can't explain at all. Whatever definition.
Why?
I'm pretty sure I'm wrong as well. I don't know it properly. Your voice is breaking, ma'am, by the way, a bit.
Yes, ma'am. Voice is break for me also.
Anant? Anant?
Yes, ma'am.
Anant, what is filter?
Mm, okay.
So it is an electronic circuit which is used to reduce the ripple content.
Your voice is breaking a lot, ma'am.
Yes, ma'am.
Yes,
Yes,
ma'am.
ma'am, voice is breaking.
Ma'am, your voice is breaking, ma'am.
Okay, just a second. Yeah, is it clear now?
Yes,
Okay.
ma'am, clear.
So filters are a type of electronic circuits used to reduce the ripple content which is present in the rectified output. So here with respect to filters, so you may get a question like how much percentage of ripple content can be reduced by using filters? The thing is that you can't reduce the ripples like it can't be zero. There will be ripples, but provided you can only reduce the ripples, but the ripple content will not be zero. Okay, you can only reduce the ripples by using filters. So in order to obtain the smooth DC, it is necessary to filter out the ripple content. So therefore, here in the syllabus we have full wave bridge rectifier with C filter. I have a question for you. Here in the syllabus you have C filter. C filter in the sense capacitance filter. The rectifier which is built by using a capacitance filter or a C filter. There are many different types of filters, say inductance filter, choke filters, RC filter, LC filter, RLC filters, C filter and all. Okay. So why are we choosing C filter? Why not any other filter? Yes. Can anyone answer?
Because it's more efficient than others.
There is a reason behind that. Yeah, it is efficient also. Any other
Capacitance
answers?
blocks DC and allows AC.
Okay, then any other answers? Any other answers? So this is the circuit of a bridge rectifier. So in the same circuit, you have to, so here in the last class, I had placed a resistor over here, right? Guys, are you there?
Yes, ma'am.
So across this load resistor, we used to measure the output voltage. Okay, either you can write the circuit like this, or you can also write like this. In between these two junctions, in between these two nodes, you can place a resistor. Both are one and the same. Whichever way you feel convenient, you can write the circuit. Shall I write like this now?
Yes, ma'am.
Both are one and the same. Okay. So in between these two junctions, yeah, tell me. So in between these two junctions, we will place a resistor, and that resistance is called as a load resistance, represented by R with suffix L. So coming to filter, we will place a capacitance filter in parallel with this load resistance. Are you able to see the circuit?
Yes, ma'am.
Yes.
Yes, ma'am.
Yes,
So we
ma'am.
have a load resistor. I have placed a load resistor in between the junctions, and here you have the diodes D1 and D2 and D3 and D4. Okay. So in between the two junctions of D1 and D3, I have placed a resistor, and that resistance is called as RL. Parallel to RL, place a capacitance filter. I have represented as C. Okay. And across RL, you'll measure the output. Output voltage is measured across RL. Did you understand? Are you clear with this circuit?
Yes, ma'am.
Yes, ma'am.
So V1 represents the primary voltage, V2 represents the secondary voltage, N1 and N2 represents the number of turns with respect to primary and secondary. Here, in order to, okay, I shall explain with respect to waveform. Okay, guys, listen here. Coming to the explanation with respect to bridge rectifier with C filter. Let me explain with respect to the waveform whatever I have written. So during, okay, this is the peak voltage Vm. And this interval is called as VR peak to peak. So here, VR peak to peak, are you able to see in the waveform? VR peak to peak represents peak to peak ripple voltage on capacitor. Please make a note of all these things, whatever I have written. And from here to here, this is TC, and from here to here, this is TD. TC represents charging time of capacitor. TD represents discharge time of capacitor. And T by 2 is the time period with respect to charging and discharge. Okay. Yes. Listen now. So during positive half cycle, so this is the input to the rectifier with C filter. So during positive half cycle of AC supply, diode D1 and D2 conducts, right? Guys, are you there?
Yes, ma'am.
Yes.
Yes.
ma'am.
So during positive half cycle, this is a bridge rectifier with C filter. So during positive half cycle, diode D1 and D2 conducts and charges the capacitor to the peak value of Vm. And here, are you able to see the Vm in the waveform? Yes. So the red line indicates the charging of the capacitor. It charges the capacitor to the peak value Vm of transformer secondary voltage. And diode D1 stops conducting when transformer secondary voltage Vm, when the transformer secondary voltage falls below Vm. So this is discharge time of the discharging of the capacitor. So here the red dot, the black dotted line, whatever I have written, that is full wave bridge rectifier output. And the red graph, whatever I have written, that is filter output. Okay, that is output with C filter, and this is output without C filter. Now, you have to compare the output with C filter and output without C filter. So output without C filter you see. So here, let me open the cursor. Are you able to see the cursor?
Yes, ma'am.
Okay. So look at this cursor. So here, the waveform, whatever you are seeing, the black dotted lines, this is full wave bridge rectifier output. And with respect to red, this is only filtered output. Okay. So what happens here is, please compare the full wave bridge rectifier output along with C filter output. The thing is that, so during positive half cycle, what happens is, the diode D1 and D2 conduct. So as a result, it charges the capacitor to the peak value Vm up till here. Okay. So as the transformer secondary voltage, as soon as it falls below Vm, okay, diode D1 and D2 stops conducting when the transformer secondary voltage falls below Vm. So as a result, so capacitor goes to discharge state. Again, for the next half cycle, that is for negative half cycle, capacitor starts charging as diode D3 and D4 conducts. It charges to peak value Vm. As the secondary voltage, compare this waveform, okay, that is transform this one without filter, that is rectifier output along with capacitor filter output. As soon as it falls below Vm, capacitor starts discharging. And the cycle repeats for the next cycle. When look at the waveform here, for the next positive half cycle, diode D1 and D2 conducts and charges the capacitor to the peak value Vm. As soon as the secondary voltage, this is secondary voltage of the transformer, right? The filter without filter output. As soon as it falls below Vm, capacitor starts discharging. So this is the working principle behind capacitance filter with respect to full wave bridge rectifier. So the discharging of the capacitor continues until the diode D3 and D4 starts conducting again in the next cycle and charges the capacitor. Okay. So here VR peak to peak represents the peak to peak ripple voltage on the capacitor. Vm represents the peak amplitude of the waveform of the output voltage. Tc represents the charging time of the capacitor. Td represents the discharge time of the capacitor. Any questions?
Mom, what happens when the filter is there?
What happens? when the filter is there. That is what, when you introduce the filter, as soon as you introduce the filter, so the black waveform, whatever you are seeing, okay, with respect to capacitor filter, for a bridge rectifier, as soon as you send a positive half cycle of AC, this V2, this is positive, and here this is negative. This positive, it is connected to D1 of the diode, and positive, it is connected to N of D3. As diode D1 and D2 conducts, as soon as it starts conducting, the capacitance filter, the capacitance, it charges to the peak value Vm till here. Okay. Now we have to compare the other part. The
Ma'am, your cursor isn't visible actually.
cursor is not visible. Just a second. Is it visible now?
Yes, ma'am. Yes, ma'am.
Okay. So what you do is you compare the black waveform along with this red waveform. Okay. The thing is that as soon as the diode starts conducting, capacitance charges to peak value Vm. Okay. As soon as the secondary voltage falls below Vm, capacitance starts discharging. Did you understand? This is for positive half cycle. Coming to negative half cycle, as soon as the diode D3 and D4 starts conducting, capacitance charges to peak value Vm. And as soon as the secondary voltage falls below Vm, capacitance starts discharging, and this cycle repeats. So now you compare this waveform and this waveform, you can observe how much the ripple content has got reduced. So when you closely observe the output of the filter without output of the rectifier without C filter, you had got 48% of the ripple content, right? But when you observe the filtered output, the red waveform, whatever I have written, so that is basically a triangular shaped waveform. There, the ripple content, it has reduced than compared to the with filter and without filter. When you compare, here it is approximately 48% as given in the literature, and we have seen in the derivation also. But when you compare this with the filter, approximately you'll get somewhere around 2%, 3% ripple.
So, ma'am,
Okay.
positive and negative charging will still, charge and discharge will still happen, but it will be ripple will be reduced in C filter.
Yes, it will be reduced, but not equal to 0.
Okay, ma'am, but here voltage falls to 0 in without capacitor filter. Why doesn't it fall to 0 with the filter?
Voltage will not fall to 0. The capacitance charging and discharging will continue. It will not come down to 0.
Okay, ma'am.
Any other questions? Guys, is there any questions? Okay, I shall proceed. So with respect to filter, you don't have any derivations as such. What I'll do is that there are some 2 to 3 equations. I'll give you those equations. If you remember, that is more than sufficient in order to solve the numericals. Okay. So first equation, so the first formula is that ripple factor gamma and it is given by 1 over 4 root 3 FCRL. Please make a note of these formulas. So this is the formula for ripple factor with the C filter.
F is the frequency.
Correct. F represents the frequency of the input. Coming to second formula. Load regulation. One over 4 FCRL. Coming to third formula. To find the output DC voltage, VDC, and it is given by Vm minus V peak to peak divided by 2. So this equation of VDC we got from the waveform. So here from 0 to this part, from here till here, from 0 to Vm, this is the total amplitude, that is peak amplitude of the waveform. In order to find VDC, we will take the average of V peak to peak, that is V peak to peak divided by 2. Okay. And Vm minus V peak to peak, if you do, you will get the VDC. Do you understand? So that is what the formula I have written here. In order to find V peak to peak, sometimes they will ask you to find V peak to peak, that is VR peak to peak. And that is given by IDC divided by 2 times of FC. And the 2 which is in the denominator, I'll take it outside. The formula for V peak to peak is IDC divided by 2 into F into C. How do you represent IDC in terms of VDC?
VDC is equal to IDC into RL.
You can also, yeah, correct. You can write this as Vm minus IDC divided by 4FC. So you can write this equation in terms of VDC, that is equal to 4FCRL. Can I write like this? You may get a question, LHS also VDC and RHS also VDC. Actually, we need this formula for solving one of the numerical. As of now, you make a note of this formula. This one, as well as this one, very important. So here, when the capacitance filter value is very large, right, in this equation, when the capacitance value is very large, the 1 by 2 FC will become small, right? The 1 over 2 FC will become small. So as a result, VDC will be approximately equal to Vm during that time, when as you increase the capacitance value. Correct? VDC will be equal to, that will be equal to peak value of the output. These analysis and all you have to make a note.
Ma'am, this is when capacitance is large.
Yeah. This happens when capacitance value is, okay, let me write. As C value increases, 1 over 2 FC value will decrease. Correct? So during this, during that time, VDC will be approximately equal to VM. This is one of the quiz question. Over. Shall we proceed?
Yes, ma'am.
Yes, ma'am.
Okay. Yeah, we will take a numerical on this. Let me write the question. A full wave rectifier full wave bridge rectifier having a load of 2 kilo ohms. The AC voltage applied to the diodes is 200 0 200. What do you mean by this? 200 0 200?
Peak to peak.
200 0 exactly. So 200 0 200 represents peak to peak voltage. Did you understand?
Yes, ma'am.
It is peak to peak voltage. Okay. So if a capacitor of value say 500 microfarad is connected across the load, find first parameter ripple factor, second parameter DC output voltage, that is VDC, third parameter DC load current, that is IDC, fourth parameter load regulation. First you read the question, list the parameters whatever they have given, and then you solve. They have not given turns ratio. We will assume it to be equal to 1. When turns ratio is equal to 1, then V2 will become 200 volts. V1 will be equal to V2. Primary and secondary voltage will be equal to same. So, in order to find Vm, you know, V2 is nothing but Vm divided by root 2. Correct? So, find Vm.
Ma'am, 282.8.
282.8 volts. I want everyone to type the answers in the chat box. Many students are not responding. Vijaya Hetasvi, Bhavani Srinivas, Bhuvan Chetan, Okay, one more thing I have to tell you. The input frequency for a bridge rectifier will be equal to 50 Hertz. If they do not specify, assume it to be equal to 50 Hertz frequency. If they have given the frequency value, then well and good. If not, you assume it to be equal to 50 Hertz. C value they have given, the load resistance value they have given.
Ma'am, so it's always
So
50 hertz if it's not given, right, in the question?
yes.
Okay.
Okay.
Yes.
So find the ripple factor. How much you'll get? One by 4 root 3 FCRL. Use this equation and tell me the answer.
0.29%.
Correct. Pavan, you got 5.77. What is that?
I found the load regulation.
Huh?
Load regulation.
Okay. Next. Next question is to find VDC. Do you have IDC with you? In order to calculate IDC, you need to have VDC, correct? So what you can do is you can use the last equation which I gave, that is Vm minus VDC divided by 4FCRL. Correct? Guys, did you understand?
Yes, ma'am.
Okay.
Yes, ma'am.
Okay. This term, you can shift it towards LHS, that is VDC minus VDC plus VDC divided by 4FCRL equals Vm. So VDC, you can take it common. This will become Vm divided by 1 plus 1 over 4FCRL. Did you get? So solve and find VDC.
Hello?
Yes,
Wait,
guys,
what did
what's
I
the
say?
answer? Still you are solving? Guys, be quick.
281.4.
Yes, ma'am. 281.39.
281.39, 281.4. Correct. Others, please verify.
Yes, ma'am. 281.4.
Okay. So till this step, is it clear?
Yes, ma'am.
Okay, next. Proceed. Continue. So find IDC load regulation, third parameter to find IDC. So you got VDC from the previous step, substitute, you'll get IDC. Okay. And then coming to fourth parameter, load regulation. 1/4 FCRL. So find these two. So load regulation, keep the value in percentage, multiply by 100.
Ma'am, 5%.
Is it exactly 5%?
Ma'am, IDC is 0.14.
Correct. This is 0.1407 amperes. Next.
Exactly 5%.
Okay. Others, please verify.
Yes, ma'am. 5%.
Okay. So is it done? Shall we proceed?
Yes, ma'am.
Okay.
Yes,
Next
ma'am.
question. So this is from tutorial.
Ma'am, it's 0.5%, right? Not 5%.
The load current. Come again.
It's 0.5%, ma'am, not 5%.
Is it?
Yeah.
Yes, ma'am.
So equation is 1/4 FCRL. Multiply this value by 100.
Yeah, that's
And tell me
it
the
gives
answer.
0.5. It gives
Yes, ma'am.
0.5.
0.5% itself. 0.5.
0.5? Are you sure?
0.5%, yes.
Yes, ma'am.
0.5%. Okay. Next question. The load current of a full wave bridge rectifier with an input AC voltage of 200 volts, 50 hertz is 40 milliamperes. Determine the filter capacitor value needed so that the ripple factor is reduced to 2.5%. Solve this one.
Ma'am, if the frequency is not given in the question, we take it as 50, right? 50 hertz.
Correct. Here they have given, right?
Yes, ma'am. Ma'am, in
Okay,
case
if they have not,
consume.
yeah, if they haven't given, then take it as 50 hertz.
Okay, ma'am.
I think the load resistance value I missed. The load resistance is 150 ohms. Guys, is it over?
Ma'am, one doubt, ma'am. In the formulas you given, no, ma'am, that is already in the form of percentage, or we should multiply by 100?
No, you should multiply by 100. It is only 1 by 4 root 3 FC. What did I give? Okay. 1 by 4 FCRL. Multiply by 100, keep the value in percentage. What is the answer? Second question.
770 microfarad.
770 microfarads.
770 microfarad. 770 microfarad. Next question. Please make a note of the next question. Quickly you solve. Even this is from the tutorial. I want everyone to solve this question. I will not solve this. I shall call few students only. I want those students to answer. I don't want everyone to post the answer. I shall name a few students, only those students should answer. I'll give you 5 minutes time.
Could you scroll up? I couldn't see the question.
Okay. Vaibhav. Vaibhav Paresh, are you there? Guys, please respond. If you do not respond, then I shall mark absent for today's class. Vaibhav. Abhinay.
Yes, ma'am.
Abhinay,
Yes, ma'am.
can you give me the answer for ripple factor? Okay, sorry. They're asking you to calculate C value, right? How much you'll get?
Ma'am,
Aryan?
4.81.
Yeah, Abhinay. Abhinay, tell me.
Ma'am,
4?
4.81, maybe.
Okay. 4.81. You tell me the units. Micro, milli, mega, what?
Micro.
Where you are placing the decimal point? 481.14 microfarad. Is this the answer?
Yes.
Next. Chetan.
Yes, ma'am.
Chetan, can you give me the answer for the second sub-question VDC?
Ma'am, first part I'm getting answer is 962 microfarad.
No, Satya, please check once again.
It's exactly
Even
double of 481 actually.
no. Can you give me the frequency value?
Frequency is.
Frequency value. They have given 100 hertz.
Oh, right, I took it as 50. My bad.
That is the
Yeah.
reason maybe.
Yeah, yes.
VM is the same as VAC, right?
VM. No, VM and VAC it can't be same. No, they have just a second. 150 volts they have given, right? You have to find VM. 150 volts, whatever they have given, that will not be equal to VM. That is because this is not the peak amplitude, right? This is the
Yes,
input
ma'am.
voltage. Are you getting?
Yes, ma'am, got it.
Okay. VAC, or you can take this as V1, and that will also be equal to V2. That is equal to 150 volts because they have not specified turns ratio, right? So V1 will be equal to V2. So now, if you assume turns ratio to be equal to V1 will be equal to V2. So if V2 is 150 volts, you know V2 is equal to Vm divided by root 2. Okay. So find Vm.
Ma'am,
So once you find Vm,
278.5 hertz.
278.5 volts. Is it so? This is Vm value. Is this Vm value?
Ma'am, 212.1.
Yes, ma'am. 212.13.
212.13.
212.13 volts.
13 volts. Yes, ma'am.
Okay, fine. Next you find VDC. Use the equation. I have given the equations. Please use it. Apply the values. Get me VDC
Ma'am,
value.
VDC value is 278.5 volts.
No, I got 205.0.
205.
Ma'am,
Yes, ma'am.
204.5.
205.027.
Correct. Because even I got the same answer.
205.027.
Those who have got different answer, please check your calculation once again. Somewhere some substitution mistake or by using calculators you might have typed the other values. Please check once again.
Ma'am,
Okay.
029 is okay, no, ma'am.
That is fine. No problem.
Ma'am, I got 204.35.
That's okay, man. No problem. That's okay. Okay. Next you find peak to peak voltage. VR peak to peak.
Is it 13.4?
I'm 14.2.
IDC by FC or VDC divided by
I got 28.8.
IDC. What is the? Can you give me the equation for VR peak to peak? It is IDC by 2FC, correct?
Yes, ma'am.
You can also write this as VDC divided by 2FCRL. Okay. So substitute. I got 14.2 volts. Please check.
Yes, ma'am. 14.2.
Load regulation.
3.46%.
Is it 3.4%? Yes. Even I got the same answer. Others, please check. Please verify. Is it done?
Done, ma'am. I got 3.4% itself.
Correct. Okay. So please go through whatever we have done in today's class. So tomorrow I shall schedule a quiz. probably during night time around 9 o'clock or 10 o'clock. Is that is fine for you?
Ma'am, what time?
Around 9 p.m. or 10 p.m.
Ma'am, quiz platform.
Google Classroom. I shall share the link. Google quiz only I'll create and I shall share the link. Okay. And starting time I'll mention. I'll post it in the WhatsApp group, and the responses will be enabled for that particular duration. Once you cross the time, I shall disable the responses.
Ma'am, it will be in Classroom itself.
Google Classroom, Google quiz only I'll create. And I shall share the link
Ma'am, will there
to
be
the WhatsApp.
descriptive questions?
No, probably like a fill up the blank type of questions, like short answers only, no paragraph, no descriptive questions.
Ma'am, whatever you
MCQs, objectives, whatever I've taught in the class, same thing. MCQs, objective type questions, okay, or short answers, no descriptive questions.
Ma'am, when will you be sharing the video link for all
Video
the
link.
recorded classes? For all the recorded classes?
I'll do one thing. All the recordings I'll send it to Satya, and he will share it
Okay,
with you.
ma'am. Yes.
If that is okay.
Yes,
Okay.
Okay.
Okay, fine.
Ma'am,
Okay,
one
then
doubt,
we will
ma'am.
wind up. Yeah, tell me, Pawan.
Ma'am, that you said in starting why we use capacitor filter. What is the real reason, ma'am, about that?
Yeah, that is the question I have given it to you. You have to find out and come. Okay.
Okay, ma'am.
Please find out and come. Why capacitance filter? Why not say inductance filter is there? Low pass filter is there? High pass filter is there? Band pass filter, band reject filter. So many different types of filters are there. Why only capacitance filter? That is the question. Please find out and come before coming to the next class. Okay. So we will wind up. Next class I shall start with the next topic, that is Zener diode. Please go through before coming to the class. Once you go through the concepts behind Zener diode and how it works the basic working principle behind Zener diode, so that it will be easy for you. That is the reason. Okay. Yes. Thank you all.
Ma'am, is this the last topic in this chapter?
Yeah.
Okay, ma'am.
Thank you, 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 ma'am.